this is our manufacturing panel. Yeah, right? Right. So this is like our last panel, but if you didn't see it, I'll describe it. Fairly informal. We're going to have them introduce themselves. I'll moderate some questions. And then I think the most interesting part is opening up to questions from you. But yeah, why don't we just kick off right away?
Hi. Whoa, loud. All right. Hi, my name is Jason Kridner. I'm with the BeagleBoard.org Foundation. Started that up about 11 years ago. I'm also, but I still keep my full-time job at Texas Instruments, so I don't take a salary from BeagleBoard, who is a 501c3 nonprofit. We've been kind of growing quietly, about 25% year on year in terms of board sales. We're up to about 350,000 a year. For dev board is not too bad. Most of that is in under about 100 boards per. There's I think like one customer that's bought like 5,000 boards last year. Everybody else is like under 1,000. And so we have a pretty broad user base, entirely open source. Not a lot of barriers to entry for other people, but except we've got a little brand, and I think we're trying to change the world through open source hardware and Linux computing.
Hi, my name's Jeff Kaiser. I develop and sell open source electronics kits. I have a website, mightyohm.com, and I spent this past 7 years working for Valve Corporation developing consumer electronics, and during the time that I was at Valve, I primarily worked on a project which became the Steam controller, and so got to work on one of the largest automated assembly lines for consumer electronics in the world, and sort of in the time that I was at Valve, did a lot of prototyping in the ones and tens and hundreds, and then eventually got to work on a mass manufacturing line and got to make millions of something, and so sort of was directly involved in that whole process.
Hi, I'm Piotr Esden-Tempski. I'm the founder of OneBitSquirt, and we make open source electronics of our own design as well as for other open source projects to support their communities. We do Blackmagic Probe, the JTAG programmer debugger with built-in GDB server, which is one of the main products we do. And we are now involved in making the Icebreaker FPGA board for teaching people use the open source FPGA synthesis tools, as well as now getting into like Glasgow, Digital Interface Explorer and other projects. This is much smaller quantity than the other guys. So, we do crowdfunding campaigns for our products to launch them and get the word out, to also promote through them the open source projects that are powering the tools that we make.
Hey, my name is Mihir Shah. We own and operate quick-turn printed circuit board fabrication and assembly shops here in the US, so Royal Circuits and Advanced Assembly. We have 4 factories here in the Bay Area, Los Angeles, and Denver areas. And our main specialty is what we call home of the miracle turn, meaning quick turn, like same day, next day, 2-day turns on boards as simple as 2 and 4 layer, all the way up to crazy HDI, 4 lamp cycle, et cetera, kind of boards. And on the assembly side, we will do the same as far as literally fab and assemble just one board in just a few days. So our main business is quick turn prototype fabrication here in the US, PCB manufacturing.
Hello, I'm Nadya Peek. I'm a professor at the University of Washington, where I am in machine agency. There are 5 of us machine agents here at TEARDOWN. Why is a professor on a manufacturing panel? Good question. I think I'm currently very interested in the concept of fabricatability, or how, if you have open source hardware, what are the resources and machines that you need to be able to make that? So how do you actually go about copying in the way that is very easy with software and is not easy with hardware? But most of the time with manufacturing, my main claim to fame is that I'm very good at writing bash scripts that translate really archaic file formats into other really archaic file formats. And so I'll do that for lots of turret punches or lasers or any kind of weird machine that you might need controlling for.
I'm Steve Hodges. I'm a principal researcher at Microsoft Research in Cambridge in the UK. I've been at Microsoft for 15 years now, and prior to that, I worked at AT&T, and Olivetti had a research lab in Cambridge, and I worked at the university on and off. So I've been lucky enough to spend most of my career designing, building gadgets, which is what I'm passionate about. You know, don't tell any of my employers that I'd be doing it for free if they weren't paying me to do it. But along the way, sometimes I'm doing prototyping, but in the last few years, I've got much more involved in high volume or higher volumes. As Josh mentioned, I've been involved in the microbit, where we made, I think they manufactured 4 million microbits in total now. I've also, been involved in and had some contact with some Microsoft products which sell in super high volume, as well as, struggling sometimes with prototypes that I've built and wanting to, build them up more organically. So I'm really interested in how you scale, right? How you can come, for a given product, how you can work out how to manufacture it at a different volume, and then maybe if the product's successful, how you can transition sort of from one level of volume to the next. So that's something I've been thinking about, and I'm happy to learn more about as well.
Great. Steve, you gave a talk yesterday that elaborated a lot more on that, the long tail part. If you didn't see it, the videos should be up soon. And in that talk, you mentioned the economy of scope, right, instead of the economy of scale. Peter, I see you as a prime example of that. And a lot of what we do at CrowdSupply as the economy of scope, you listed off a number, half a dozen different products just then. It's all using the same assembly line. Can you talk a bit about that?
So yeah, I don't do it how I do it. I have my own pick and place machine in my garage. So basically, I think the history, how it happened that I'm actually doing the assembly myself is an interesting one, because I was making those small quantity open source UAV autopilots and assembling them with a CM, as you would do. But because we were making stuff and also had contacts in China, we were trying to make small quantity boards in China and had terrible experience with that. So we were getting boards back where capacitors were where resistors were and vice versa. And even though we tried to provide all the documentation necessary, it was 2010, I know things got better since then, but that was my experience back then. So we were like, we have to have the CM locally. We were in the Bay Area, so there are several CMs, we could use them. We are doing assembly. So, and then I left the Bay Area to Oregon. There are some CMs, but they are very expensive. So in about a year, I spent so much money on CM because I did it locally as I would spend on a full pick and place machine line myself. So basically the decision was, what do we do? And we decided to get a pick and place machine. And I started doing the assembly that way because of just the economy of the quantity we are producing, because it is in this band above 10 and below 1,000, where the spin-up costs and like the complexities of, do I buy a plane ticket to go to Shenzhen to do it there? Does it make sense? It's like, in many cases it does. And in many cases, if you have those contacts developed, it makes sense. So now it is like grandfathered in a certain way, so the machine has to work for itself. So it has to earn money for itself. And so we keep doing that. I'm not sure.
Machine. Feed the machine. Yeah,
feed the machine. And this is the question: when do you make the cutoffs at the quantities that you need? It's like, for example, Icebreaker. We did. We are still in the middle of fulfilling that crowdfunding campaign, and so there's a ton of very simple PMODs that plug into it. This is something I ended up ordering from China because it's simple. I don't have to like be too scared that I get something that won't work exactly how I need it. So I did make that there because that worked out. But the Icebreakers, for example, I have parts that I would have to ship across borders several times and deal with customs, delays, and payments. So doing it myself in my shop where I know how the machine is set up. I can control all the parameters of doing the assembly, and having the full vertical integration really pays off.
Mm-hmm. So, Mihir, you mentioned that you're based in the U.S. We're diving into geopolitics now a little bit, but
tariffs have been good for us. Yeah.
Right. What do you foresee? At a coarser timescale.
So I'll just give everyone a really brief overview of the industry at large. In 2008, there was over 2,000 quick-turn printed circuit board shops here in the United States. Today, a decade later, roughly, there's about 135. So a 95% reduction in the supply, yet the demand is at minimum 2 times higher because of things like IoT and just the general idea of democratized hardware. People are designing more people are designing more, etc. So how does that make sense in any sort of economics like structure? A large part of that can of course be attributed to China. But the other thing is also the hardware people are designing is more and more complex. And yeah, there's a whole military aspect to that. Fine, there's one portion that you cannot go overseas. But even people that are designing, they're looking for high quality and they're looking for speed, and the price they're looking for is fair. And that is really the market that has shown to be the most sustained. And that's what's really kept a lot of the US guys in business. And then of course going to the more high-end stuff, which a lot of people here are designing in larger quantities. Like people are designing FPGA type boards without having some crazy advanced degree, and they're putting really, really tight BGAs on their board that may need to be 4 or 6 layers or 8 layers with tight paired and blind vias, kind of things like that. So they're choosing to go to a US manufacturer because if you have to spend a couple $1,000s, it's generally better to do it with somebody that you know where they're located, you can talk to the support and things like that. And then you have people like Oshpark, which is probably the best resource that's come out of the United States for that market, that people are like, oh, I'll go to China. Because if you actually add up all the spec, what Oshpark gives you versus what like a JLC PCB gives you, like high TG, ENIG finish, getting your boards in like a week, and the customer service and support, etc., it's actually far cheaper. So I really encourage people to actually do that comparison, but it's a whole different thing when you compare apples and apples.
So both of you guys, though, you really aren't necessarily at the far extremes from each other, right? I mean, your pick and place machine was probably still pretty expensive, right?
I have a lot of thoughts on that. I think you're doing it wrong, but yeah.
And the stuff that you're doing, you're doing a lot of volume, but your real focus here is like quick turn and speed.
Quick turn, low volume per order, but the overall volume of boards that we do is quite high.
Right.
But the order volume on these are like 1 to 10.
So why do we have 135 folks doing that when we should have 135,000?
Right.
Right. So where's the RepRap for pick and place, right? So we've seen the 3D printing started to take off now, but that started with the movement of RepRap and building the demand for the users to reproduce their own machines, right? Why aren't we reproducing our own electronics in the same way?
So CMs, there are thousands in the US. Board shops, I'm saying there's a low amount. Because to run an assembly shop is easy, and that's the other thing. A contract manufacturer is one of the worst businesses that you can go into if you're trying to do any sort of scale. They're like sub 5% net margin. The only way a CM makes money, and this is especially good for people that don't do any sort of volume, is they make their profit not on the pick and place, because how much can they possibly charge you, or how much are you willing to pay for someone to place a resistor on a board? Probably not that much. It's on the order of cents, maybe low double-digit cents. So the only way a CM makes profit in their business is on the markup on the bare board that they outsource. So they come to us and they strangle us and try to get boards for $200, and then they add a $600 markup that then gets put to the end customer. That's the profit for their business. So doing it at scale doesn't really work, but there's thousands of these guys that have 30 employees, sub $5 million businesses that do that. But at scale, it's a whole different ballgame. Doing the quick turn stuff is one thing that very few shops do.
We've seen some really kind of I don't want to disparage anyone too much, but some efforts to actually do manufacturing of PCBs, right, at the individual level, right? So not just doing the assembly, but actually doing either milling. I mean, we see a lot of use of laser cutters, a lot of other technologies where people are building up PCBs in their own. Some of the uglier ones, right, include squirting ink, right, conductive ink. Yeah, exactly. So you could.
So Nadia, this is kind of your wheelhouse, I feel like. Machines, Jason asked about the RepRap of PCB and boards.
Yeah.
What's up there?
A long time ago, I designed, together with Jonathan Ward, a milling machine that was makeable on another milling machine to mill circuit boards. And the idea there was to make crappy circuit boards in 10 minutes rather than semi-crappy for circuit boards in 12 hours or whatever the fastest turnaround you can get now is. And there I think it was largely a failure because even though, and that's really informed my ideas about what's possible for open source hardware, because even though we documented that project to the extent that we thought was necessary for someone to replicate it, people didn't actually replicate it because the amount of tacit knowledge that we already had and were able to invest into the machine building process was far higher than someone who's like reading through a description on the internet and assembling and milling parts and assembling them. And so what for hardware in electronics, there are actually a lot of really explicit things like boards are 1.7 millimeters or boards are 3.2 millimeters. Like there's all these really explicit requirements that everyone agrees on. But as soon as you start manufacturing other things like machines, there's suddenly a lot of things that people don't agree on. RepRap is interesting because the thing that they seem to agree on is you have to make explicit the things that you can't make yourself. So the idea is you should be able to make as much as you can as possible. As much as possible of a RepRap, and everything else is a vitamin, like the things that your body can't synthesize, you have to eat. So the mechanical vitamins of a RepRap are things that you have to buy, and that I think is not something that is really well understood yet. Like, what are the things that we can make, and what are the things that we have to buy? And if we buy things, how do you do quality control in low volume for that kind of process? How do you do quality control at all when you're not doing probabilistic quality control?
So was it an issue of you needed better? If you had better documentation, do you think people would replicate it, or do you think that even if perfect documentation?
I think that basically by the time you had enough, this is my read on it was, by the time you had enough skill to be able to mill, assemble, make the controller board, like connect everything, run the software, you had enough experience with all of those processes that you probably wanted to design your own machine, or you wanted to be able to make it slightly different to better accommodate whatever the thing is that you were trying to automate. And so the direction that we went in after that was, instead of making these like simple machines that people could replicate, we were interested in making infrastructure to make it easy to automate other arbitrary things. So how do you make controllers that are extensible and reconfigurable? How do you make mechanical modules that are extensible and reconfigurable? I got yelled at by a lot of mechanical engineers. They're like, every time you introduce a connection, there's a point of failure, which is true. But that's kind of the same argument that they made about packet switching networks, and like, let's see who won that one. Right.
You should see how many connections there are in this pick-and-place machine I have. It's ridiculous. So it's like the wire harnesses go from like the power driver board over 5 connections and connectors until they end up in the motor. It's crazy. What machine do you have? It's a quad. It was bought later by Tyco, and then now there's only a company in some in Massachusetts that's it's PPM. Precision placement machines. They buy old machines, refurbish them, rebuild them, and put new computers in them. And this is the machine I have. And this brings me like a little bit. This is apropos because this came up like 15 times when I was here, and I see that on Twitter. That question so many times. Do you? Yeah, the people are already laughing because I complain about it. People are asking, it's like, do you like measure all the parts every time you pick them up, or do you just rely that it will pick up it accurately enough and not scan it at all? This is a misconception generated by OpenPNP and Neoden machines and all the cheap machines, because they don't have any sensor that when you pick up the part, either you are very slow and go to the upward-looking camera and measure it and then place it, or you just pick it up and just hope for the best, which is a terrible idea. No proper machine does that. They have some way of scanning the parts always. So they have something either on the head, like my machine has like a beam that shines and makes a shadow that you can measure where it is on the nozzle, or you have a camera that can look sideways on the part, or you scan the part in flight. When you fly over, you don't stop. The vision is fast enough. We have the tools. OpenPNP I think, could do that if they really knew that this is actually an issue. And I think this is a misconception in the DIY machines.
It's also an architectural problem, right?
Yeah.
There's state in the machine. So you have, if you want to do any kind of feedback loop through computer vision, you have to understand you have to stop the machine while it's moving somewhere. And by nature of how G-code and machines work, you don't know where it's going. So you have to have like a stupid way in which, instead of having like a nice hierarchy of how process calls are being made, you're constantly going all the way up and down the stack, which is dumb, which is why maybe open source people are like, yeah, maybe we should wait for that.
So
I think it's understandable.
So Nadia, you brought up, we'll have plenty of opportunity to talk about that. Nadia, you brought up failure analysis.
Yeah.
Jeff, I watched your video about the Steam controller and the machines that test other machines. It was like machines hugging each other or like being sensual with each other. Tell us about your design, your production line.
So when I worked at Valve, we built this enormously spatially large and also very complex automated assembly line. And to my knowledge, it was in the U.S. Yeah. So within the U.S., I'm pretty sure this was unprecedented at the scale that we did it. And that, yeah, there were machines that tested products. The machines weren't testing each other, but they were testing products. And it was an interesting experience because automation gets talked about a lot. And I think there's a lot of interest in automation, particularly within the US as a way of doing cost-effective manufacture. And I think automation is very interesting. Automation has a lot of trade-offs, and there are pros and cons to automation. And one of the things that you run into is that unlike robots, humans are very perceptive, they're very flexible, they're very reprogrammable, and they see things. You can have a jam in a machine somewhere, and a human operator might walk up and they hear the noise that the machine's making because there's a part jammed, and they're like, oh, I need to fix the jam, and you sort of just flick it, and the line kind of continues on. Robots are really bad at doing that, and I'm sure that there are groups, companies that are trying to solve a lot of these problems, but especially when it comes to things like surface finish, like cosmetics, machines are not super great at doing cosmetic inspection, especially if the range of issues is not super well known. If you know what the issues are, then yeah, robots are great. Computer vision is great. But yeah, I think that it was an interesting experience in trying to figure out what the right level of automation was and like what robots are good at doing. They're good at doing things very repeatedly, doing the same thing over and over and doing it very fast. But it's when you have when you're designing an automation line, you may not know the types of failures that you're likely to encounter, and that's kind of hard to anticipate. Like if you haven't ever built that type of product before, how do you anticipate all the possible failure modes and build robots that will exercise all those failure modes? So that was certainly something that was interesting. And there was actually an episode of the Amp Hour, and I think it was Chrissy Meyer? So Chrissy Meyer was on an episode of the Amp Hour and talked about issues that she encountered during her career at Apple and other manufacturers. And so much of it hit home because she mentioned that like wet processes are sort of your worst nightmare in manufacturing. Like anything that uses glue, like consumables in general are hard, but anything that uses liquids is incredibly challenging. And that's something that I think is sort of unique, that until you've been there, you don't know how painful that is. But that was also a kind of an interesting lesson learned. If I could go back in time, I would make a lot of very, very different decisions because of how challenging it is to like dispense fluids properly and do things like that time and time again. And those are sort of the things that you learn by being there and actually designing those systems, right? You might change how you do that the next way around.
I mean, we talked a little bit about those vitamins, right? So the vitamins I feel like that's a more solvable problem in a lot of ways than the individual democratization of manufacturing, because if you know what the vitamins are in the semiconductor world, it's a very wet process, and we've kind of figured it out. All right. I mean, when you make millions and millions and millions a day, right, you see all the errors. You talked about you have to see the errors to find them. We've seen a lot of them, right? You do the process variations. You test at the corners, right? You have the machines to test for all the types of failure modes that you would, that you've encountered over years and years of an iterative, process step improvements. But if in order to kind of leverage that scale of manufacturing, you've got to make millions of them in order to leverage it. Right, so we that vitamin, right? But figuring out what that right vitamin is, so that it really democratizes things, I think is a real challenge for it. I think we're wrong if we kind of punt on that problem and don't try to enable individuals to have the same access to manufacturing that we do.
But I think a very good example is Prusa, for example. It's like. The 3D printers is a very good example of the democratization, in my opinion, because so far I still don't have a 3D printer because I hear too many horror stories. But now friends are getting the current Prusas. They just work out of the box. So they produced enough of them. They had enough users use them, find all the corner cases, and they adapted the design many times until the Prusas became reliable machines. You probably know better about this kind of machines that are for users.
I think that testing and tuning is an important component of it. I don't know. I'm kind of reminded now of, I was on another panel at the White House, the previous administration. And the whole idea of the panel was like the White House had heard about this thing called the maker movement. They're like, ooh, makers. What are makers going to do? And we want makers to grow up to be manufacturers. And I was a little bit contrarian on the panel because I was like, manufacturing is fundamentally super broken. Like, we have to offset the spin-up costs with this giant economy of scale. So unless you make $1 million of something, you can't make money off of it, because doing the first thing the first time takes all of this time where you're constantly banging your head against all these problems that you're encountering. And maybe there's a way that you can test for it. You have tests that you can run to make sure that things aren't going to fail in certain ways. But I think that there's just something really wrong with how we currently manufacture things. Being able to do tuning and constant testing as you're doing the production, or being able to do simulation. Civil engineers don't do a bunch of tests first. They just build bridge. And so being able to do simulation and tuning and testing along the way are things I think that really need to be built into the infrastructure that's internal to manufacturing. And before that changes, a lot of these other things can't. And the benefit that Prusa has had is because so much of their tooling and so much of their process is tools that they've developed themselves in-house, they can build all of that software-inspired unit testing into their production line, and that allows for reliability to come even from a relatively low-volume product.
I think they're also making a product that people want, and I think
guys, I think we should make Steve say something.
Real quick, I have very strong opinions about desktop milling machines for PCB manufacture, and I have a bit of experience. I haven't used them all. Unlike 3D printing, that's an area that I don't know makes sense. And I'm actually curious to hear other people's thoughts about that, because it seems like with Osh Park, with overnight PCB fabrication, which is it's still quite expensive, but is available, widely available. I don't know what the situations are where it would make sense for someone to be milling PCBs at home. And I've seen a number of products in that area, both fairly inexpensive, kind of targeted at makers, as well as really, really expensive high-performance machines that are kind of targeted at larger corporations. And I think 10 years ago, it was super different. I don't know if anyone remembers batch PCB. It was not fast, right? It was faster than some of the alternatives, but it wasn't really fast. I think now that you can get a PCB within 2 weeks, rather than kind of mess around with my home PCB mill or my semi or even professional grade PCB mill, it's much better for me to be doing design or ordering parts or going outside. I don't know, doing something else. So it's not really clear to me what niche that fills. Whereas 3D printing, I think, is the total opposite. 3D printing is awesome, and you can do a bunch of stuff, and it totally makes sense. And those parts are directly usable. PCB mills, a lot of times, I think I'm not really aware of a PCB mill that has a good through-hole process. And That's like so fundamental. Double-sided is a challenge too. And trace and space, they tend to be pretty chunky, and the world is not at chunky anymore. You're doing surface mount, you're doing 0.3 millimeter pitch, you're doing BGAs. Like the PCB mill industry, and again, I don't want to discredit the guys that are trying really hard to make that work. I just don't understand how that makes sense.
Why would I ever 3D print anything when I can just go online and order it and have it shipped to me overnight anyway? So why would I 3D print anything?
Because it's fun.
So maybe that's why people use PCB mills, right?
That's not fun. I've done it. It's not fun.
So if you seriously want to ask the audience, we should do it before we tip the discussion any further in one particular direction. But like, who here thinks that PCB mills are good for prototyping? There's a few. And who here thinks that PCB mills are not good for prototyping? More. Cool. So I don't think they're any good for prototyping, but I thought that 10 years ago. So for 15 years, for example, whenever anyone says, hey, should we get a PCB mill? I've said, really? But I also, so one of the observations I made is a lot of people that I work with, I work for Microsoft, right? So they come from a software background, and with software you design your product, and when you design your product, what do you need to do? You need to make copies of it and distribute them. And with software, that's actually quite easy. I mean, it's not trivial, but it is relatively easy. You make a copy, and guess what? You can check to see if it's perfect or not. It probably was, but maybe you just double check, and if it's not, you can start over again, and you've got a perfect copy. And this replication challenge we have with hardware, it doesn't matter how much you spend. You need a whole process which is customized for each piece of hardware typically. And no matter how much you invest in that, when you then make a copy, guess what? It's not the same. It's not identical. So it depends on the, it's different for different aspects of hardware. And I think in the case of bare PCBs, I don't normally worry. I get I check the box if it's even an option these days. Usually it's default, right? I get my bare board tested, but like I'm going to assume it's a pretty good render of my, my Altium file or my Gerber file. So I'm not worried about the replication of PCBs. I don't use a mill. I'm shipping the stuff out. And then when it comes to PCB assembly, well, there's still, my board doesn't work. Well, maybe it was misassembled. Maybe there's a solder bridge somewhere. But I'm also reasonably confident about PCB assembly. So we talked a lot about PCB bare board manufacture and assembly. But for me, they're not really the bottleneck anymore. So if you look at, and for products like a lot of the crowd supply products, well, that is the main manufacturing process, right? So, and I think that's what enables some of these products to be viable in lower volumes, because that technology is reasonably, well understood now, and it scales. I think PCB, bare board manufacture and PCB assembly kind of scales. Now, obviously, if you make more of them, you get more economies of scale. The unit price comes down, but it doesn't stop most of us. Maybe the few people, people using mills don't do this, but most of us would use the same fundamental process for building our first prototype that Apple use in however many tens of millions of iPhones they make every month. So I feel like that scales. For me, the bottleneck might be elsewhere. And so I think enclosures is a big deal. And we talked about 3D printing, and I have to confess, I'm probably not up to speed with the latest developments in 3D printing. But certainly until recently, even 3D printing, it's great for prototyping, but it wouldn't necessarily, depends what the product is. I wouldn't ship a product because the finish might not be good enough. The material qualities might not be suitable, right? I might not be able to get the wall thickness I want, or it might just not be strong enough. So I think that is slowly changing for 3D printing, but I think that's a plastic type enclosure for me is a challenge, because when you get to 10,000 pieces a year, you can afford the injection molded tooling probably, but when you're just thinking about your first 1,000 units.
Also mill enclosures.
So you can make them out of wood, right? You can you can laser, you can sure. I mean, milling. I think this is all really interesting. Like, what kind of for what kind of products do you think milling is cost effective? Yeah, I guess if you're milling wood and plastic, it's pretty fast, right?
iPhones and all those Mac computers, they're milled.
Yeah, like a huge volume, absolutely.
Yeah, but they're CNC milled.
Yes.
So they're. I want to hear you. Oh, sorry.
Sorry.
In defense of milling machines, I guess PCB mills.
I was talking about PCB mills, right? Not milling machines full.
Well, I think that there's a misnomer. Maybe if the workflow that everyone is familiar with is that the mill is being used to mill PCB boards, then then you're like, okay, this is actually not a very good way of making PCBs, and that's been well established by the market. But milling as a way of making things allows you to do things with high accuracy, high repeatability, and once you have the vocabulary of milling anything, including PCB, you can also start milling other stuff. So if you wanted to make a gigantic heat sink, or if you wanted to make enclosure, imagine if you wanted your enclosure to be transparent. No thanks, 3D printing. So I guess part of the argument that I would make is understanding how you make stuff, including how do I buy stuff that I'm going to be putting on the thing that I'm making? How do I order something? Actually, ordering PCBs might be like very obvious to everyone here, but I teach undergraduates electronics, and that's like a pretty scary, like if there's money involved, you know, telling them, why don't you just like make a board that you can put this one transistor on and also like a power connector, and you can make it on this mill now. Then you start, you know, it's sort of like a, how do you scaffold learning in that regard, and how do you get people to make more stuff more quickly and then build confidence so that more people engage in the diversity of production? Okay.
I would like also to defend the PCB Mouse in a very specific, really tiny niche. It's like Joe Fitz, you might know him, Security Fitz. His class is doing security in hardware. You need one adapter board for this specific thing today, now, in half an hour. That's a perfect application of a PCB mill. You don't want to wait a week or even a day for that part to come here that you ordered from a PCB manufacturer. But they're very, or that.
I think we discovered the Emacs versus Vim of hardware.
I would like to say that I think my argument is that PCB mills as part of product development, especially beyond early stage, probably doesn't make sense in my opinion. I don't disagree that as a vehicle for education, I definitely see opportunity there. And as a vehicle for doing kind of one-off, there definitely is a niche. I've designed antennas. I've used PCB mills to do antenna prototyping. That's definitely a niche that there are machines that are designed to kind of fulfill that niche. But yeah, when you have to modify your design to kind of work with the capabilities of the machine, that gets old really fast, and that's been my experience.
Okay. I agree on that one. Mihir and Jason, you both talked about growth and you know the lack of supply and the growing demand. How does that work? You mentioned 25% year-over-year growth in sales in Pocket Beagle. Earlier, I don't remember which. I think it was the previous panel. Maybe we discussed how Linux, embedded Linux, which of course is kind of pioneered by Pocket Beagle in a way, or by BeagleBoard, is about to make a breakthrough. Is that going to affect your business, and how do you get your stuff manufactured right now?
I mean, for us, I mean, we have manufacturing partners, and the hardware is kind of the easiest thing for us. I mean, all we're complaining about all this hardware. I mean, the hardware is easy. The hard part and our bottlenecks to innovation is software and collaboration with our community. All right, if I could put version 1 in 100,000 people's hands, and they can find all the issues, and then just all of a sudden hit reprint, and they'd have version 2. Right, and we found all the bugs, and that would be great. But trying to find a rollout process for a new platform where you want to get into the right people's hands to find the issues, and then spin, and then a few more people at software, and it's always the software development that is our barrier to new product introduction. And trying to solve more problems for people. So we'd be spinning boards every week if it wasn't for software.
So how many? When's your next board coming out? Do you have what's the next version?
So we're working on BeagleBone AI right now. So we've got a bunch of boards that we've built, and we're giving them to try to give those to people right now for alpha testing and getting feedback on those. We're probably going to launch in about September. We've had boards since November, so we'll probably been 10 months of having the boards before we actually start shipping them in volumes.
So I'll look for those files in my email for us to build.
So we can get the nice AR video going for that. Yeah, sure.
Was your question more on like
So-
what's stalling growth in manufacturing, or was it?
I guess where's the growth coming from, and is embedded Linux going to have an effect there that would impact your company?
Yeah, ultimately, I think all those things. Anything that allows people to create more and democratizes hardware even further, yeah, totally, has a huge impact. IoT has been massive. And also the amount of venture capital money going into these kind of startups and going into these kind of ventures is insane in San Francisco and LA and New York and all these other cities. And we're kind of tapped into that. And you see these startups with like $100 million funding for sensor companies and this and that a huge chunk of that is going towards hardware and quick iteration, where your time is way more valuable than waiting even 3 days for boards. So that's where a huge source of growth in
Okay,
orders.
quick poll of our panelists. How long is the term IoT going to be around for?
Yeah, I keep it.
Oh, wrong question, because I thought we were going to talk about AI.
Maybe too long.
I don't use it.
Pass.
It's going to be a term like IPv6.
All right, thanks.
I think it's going to be around for a while, the term, yeah. It doesn't mean it's quite vacuous, right?
Yeah,
so
it's just a generic.
yeah. I don't know if that's good or bad. Is that good or bad?
Send his microphone.
We have things, we like our things to talk, right? So they talk to us, they talk to the network, preferably the network, because I don't want to hear my things talking to me anymore. They need to shut up.
Okay, let's open up the floor to the audience. I don't even know how much time we have, but first question. Yeah.
Yeah, I'm a semi-retired EE and new to Portland, and interested in how a person with RF and microwave experience might contribute to this chain.
So I'm an RF and microwave engineer. At least I started my career there. I think RF continues to be something that a lot of people consider black magic, and so there's always a need for people that understand that. Particularly if you look at the number of 2.4 gigahertz devices that are operating in the ISM band, there's so much out there, and I think still RF is not well understood by most of the people that are using it. I've seen there's a lot of pitfalls that product teams fall into. You think about like antenna placement and sort of how industrial design relates to opportunities for antenna placement, and even just fundamental sort of I suspect that the vast majority of companies and product development teams that are putting 2.4 gigahertz radios into their products have never done a link budget. And that's a very, 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 very bad idea, particularly if you're going to ship a lot of something and it's very hard to make changes, and it usually is. So I think that there's a lot of opportunity. RF, I remember when I was in grad school, we were worried that hardware RF was going away. It was all going to be software-defined radios. It was all going to be software. So why do we need any RF people? And that was 20 years ago, and we still need RF people. In fact, I think we need them more because every product has RF. And I think there's a tremendous opportunity, especially antenna design is especially still black magic. There are very few people that are comfortable working around antennas. I'd say the vast majority of antennas that are implemented incorrectly or poorly or in a way that is hampering performance. You see a lot of products that they like that kind of customer perception that RF is flaky is because the engineers didn't do a good job designing those products. And of course, these products operate in really hostile environments too. So I think that my experience has been that having an RF background is very helpful to fall back on, because there's always going to be some like late game crisis in the RF space, and there's an ever-present need for people that can solve those problems.
So I think there's not enough. So what is actually like enabling and like fueling a lot of these things that we are making? It's are more designs that use certain technologies and are shared and are documented and are written about, and there are videos about it. There are more slowly like channels on YouTube coming up of actual people that really know what they're doing, making videos about what they really know about and sharing it and putting it in formats that are not old dusty books that people are having trouble parsing. And that books that require a lot of background to even parse these content of those books. Especially, I think RF contains a lot of really hard physics background that is necessary, and bringing that easier to people that might not have that background. It's like, I'm a software engineer. I shouldn't be doing any of this. So I learned pretty much everything from wonderful people that shared their knowledge in form of objects and blog posts and videos. And the more of that, the more the community gets better at this. And then the design, because of the democratization, this is what I think you are talking to. It's like we have tons of the IoT devices that have RF in them, and people are just copying someone else's design that's the best they can do. And it's still badly placed. It has like a backplane in there or something. It just doesn't work right. It works well enough that on the bench it works, and that's it.
I think you could start by going to some of your local hacker spaces, maker spaces, and teach them how to use the basic tools for getting some visualization, network analyzers, near field probes, and just get some idea to actually build some visualizations. And talking about certification processes, right? The FCC, CE testing stuff doesn't have to be that complicated, but it's a huge barrier for a lot of us, and a lot of us don't know how to approach that. So if you have a little bit of regulatory, look at the stuff that's needed, then helping to walk people through some of those processes would be tremendously valuable, because otherwise they're going to spend way too much money and not be ready for it when they're there.
Yeah, I totally agree. I became kind of the lead regulatory compliance guy at Valve because I was the RF guy. It's just, there's tons of overlap there. And the ability to go to a lab where a product's being tested and kind of call BS and say, yeah, what you guys are testing it wrong, or these results don't make sense. The ability to sort of understand how those tests work and how they're conceived. I think there's a huge amount of overlap between regulatory compliance and RF design. And if you have the RF side, I think it's pretty easy to kind of start reading the rules and understanding the regulatory side.
You're supposed to disagree with Next question. One more. Yeah.
And Jason's wrong.
Oh, Jeff, you mentioned that that RF is perceived as flaky by consumers or even other engineers is actually a misconception. Can anyone think of any other common misconceptions about the engineering discipline where people have just come up with the wrong understanding because of a bad practice? I can elaborate, and
I mean, at least as far as what it takes to manufacture a PCB, that's probably one of the biggest things that nobody really learns in school. And people don't realize that even a 2-layer board goes through like over 90% of the same processes as a 10-layer board with crazy, crazy stuff going on. It still has to touch over 20 individual people, go through all these expensive machines, wet processes, and that's time being taken away from other orders, and then everybody wants it for free. And there's like huge costs associated with this, especially when you're in like the US, but that's why you kind of offset that with different quality and things like that, and you wonder how can China do it so cheap. And I mean, it has to do with subsidies and labor costs and quality and things like that, but just how much complexity and money and capital intensiveness goes into running a printed circuit board manufacturing shop is crazy. I mean, we just bought a new laser 2 weeks ago. It was $1.2 million just for a laser. We have 7 of them, and drill machines are over $600,000 a piece, and it's just like how much money and time and effort goes into making even something as simple as a quick 2-layer board. And that's why people like Oshpark and these guys exist, who can kind of amortize the cost over a group of people on like a panel. But knowing the complexity that actually went into it is pretty interesting.
I actually have 2 examples that are not so customer facing as within engineering that are, I think, misconceptions. And I think one is that a lot of people think regulatory compliance is bad, right? It's overhead. I think that it is true that there's a lot of red tape, but I also think that there's a lot about regulatory compliance that actually results in you making a better product. Like especially a lot of the European requirements, like CE has product safety requirements that, you know, are pretty generic, but are well-intentioned certainly. And I think that as an engineer, you have kind of a responsibility to make a safe product. Similarly, a lot of the electromagnetic compatibility stuff, like ESD, the requirement is that your product survives ESD. That's important. That's actually good to make products that survive ESD, because a lot of times the goal to pass is that the product works as intended, and that's really good. The other misconception, that maybe this is my misconception, or maybe it's a misconception in the industry, but when I started the industry, quality was always seen as kind of like, oh man, I've got to fill out all this paperwork and I've got to do a PFMEA and all this stuff for quality. I used to think that until I was sort of responsible for shipping a high quality product. All of a sudden I cared a lot, suddenly cared a lot about how you enforce quality and how you get manufacturers to consistently make things of a very high quality. And suddenly I went from sort of dreading and maybe not thinking that was something that was really how I wanted to spend my time, to something that I spent time on and I became very passionate about, because I realized that it was valuable. And it took me a while to kind of come around to that, but eventually I did.
Yeah, to this point, I think what is missing in our, especially in talking about this like crowd supply, small manufacturers, smaller groups, communities, we are still lacking a lot of tools in that realm. It's like, do you have like a 10,000 volts like a zapper to check your boards that they survive it? Do you have an anechoic chamber? Do you have a Faraday cage to do RF testing?
A 3-year-old.
Very good, yeah, quality tester for sure. Not everyone has those.
Right.
But yeah, but we are slowly getting those tools. Actually, it's like we have some of the like current use tools, and tools like HackRF are helpful, and we need to focus more on using those tools and describing how to use them to do and people like you should write about this and share it with the people that don't have the background.
So Steve or Nadia? Yeah.
I think that something to be taken into consideration for how things get made is that there's this concept, it's like Fordist concept, that you have a task and you break it into small subtasks. People do those subtasks efficiently, and a project manager sticks everything together, and then you have like a good product. But there's high interrelation between all of the processes, and through the whole network of assembled ad hoc actors, there's risk, and risk is borne by different people more severely. Like you don't really, you sometimes hear about like Frank Gehry getting sued over a design, but you much more often hear about some subcontractor that didn't get paid because they're whoever ordered the parts from them like went bankrupt, or some horrible thing down the line where a bunch of people didn't make money, lost their jobs, and risk is unfairly borne by them. And how do we, as people interested in manufacturing and maybe the future of manufacturing, understand how to fairly distribute risk in a new kind of project network where we're dealing with crowdfunding, where people are funding the work, the manufacturing from as a consumer, where you're dealing with people who are doing things in low volume, so risk isn't amortized over high mass. So I think that the question of like what are the aha things that people don't really think about? I think it's like almost every. People don't understand almost anything, and how do we make that better?
We're gonna have to end there. Those are good questions to think about. Thank you, Nadia.